Okay, today we're going to be doing open resonators. Woohoo, so fun. So what's an open resonator? An open resonator is basically like a pipe, alright? Or it acts like one, but we're going to keep it simple here because simple is good. You will notice a pipe drawn right here. The reason why this is called an open resonator is because it's open on this end and it's open on that end. That means air can go in one side and out the other and vice versa. If you cut this in half this way, you would see it look like this. So pressure waves of air, right, which is what sound is, can pass through either direction. It does not matter which way. Okay, some instruments work this way and some work a different way. One example of an instrument that works this way is the flute. The flute works this way because both ends of the flute are open. Okay, there's a hole in this side right there, and there's a hole on the mouthpiece. Now, when you play the flute, remember you don't actually put your mouth over the mouthpiece like this. You don't cover it up unless you're a really bad flautist. But what you're going to do instead is blow over the top of it like you do with a soda can, right? To make that sound. So what that's going to, the effect is going to have is it's going to have open and air can move in and out on both ends. The waves will be going down this way and they will be bouncing off and heading back. But remember that when they bounce off, what's going to bounce back is the opposite, right? Just like when you have the string and you have this wave going this way, when it bounces off, it's going to be reversed. It's going to be the same thing. So when this wave goes to the left and it bounces off, we're going to have like a gap. Does that make sense? It's going to be a rarefaction instead of a compression. All right? And that's how open end resonators work. They work by bouncing the sound waves off the ends. All right? So let's take a look at one. Here are a series of open end resonators. So fun. So we're going to first talk about the fundamental. Remember, the fundamental is the same thing as the first harmonic. Let's abbreviate. Okay, so what is going to happen? So at the end of here, this is where the pressure is the highest. Let's pretend I just blew into the flute or whatever. Okay, so here's the wave. The wave is going to go across, and once it hits the other side, it's going to invert, so it's going to look like this. Okay, and once it inverts, it's going to do the same thing on the other side, and this vibration makes sound. Okay, so this is the first harmonic. You will notice that there is a node on here. There's a node in the middle. All right, because the pressure wave coming from the front and the back cancel out in the middle, so there's no vibration directly in the middle. Okay, and that's it. So what we want to talk about is these pipes are length L, right? We're going to use a cursive L so it doesn't look like a 1. And we are going to relate L to the wavelength, okay? So the wavelength is for one wave. Do we have one full wave inside of this pipe? No. No, we do not. We do not have a full wave. We have half of a wave. Now, it's drawn with its mirror image, so maybe you're confused. But if we look at this wave here, this wave starts at the top and it goes down to the bottom. Okay? That is not a full wave. That is half of a wave. So that means the wavelength, we would need a pipe that is twice as long to get the other half. So the wavelength is going to be 2 times L for the fundamental frequency. Ta-da! Alright, now let's go down here for the first overtone or the second harmonic. Alright, we'll just slash in between, whatever. So this is going to be the next highest wave that is able to resonate in this tube, okay? Now if I bumped the frequency up just a little bit, it's not going to create a standing wave. But what is the next standing wave that is possible? Well, on the ends we're going to have our antinodes, and so what is going to happen is we're not going to have one node in the middle, we're going to have two nodes in the middle. Ta-da! Alright, so what's going to happen is it's going to go up, and then it's going to go down, and that's it. Alright, same kind of thing here. It's going to go down, and it's going to go up again. Alright, so remember these are two separate waves, right? But they're drawn so that it fills the space a little better and makes more sense. So we still have two nodes now, alright? Two nodes. Alright, so question is, we're still length L. How long, or what is the wavelength going to be in relation to L? Do we have a full wave? Yes. Yes, we do have a full wave. Alright, let's look at, well, I guess we started here last time. Let's do the same thing. Let's follow this one until we get a full wave. Do, 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 do. Hey, we have one full wave, so that means the wavelength is going to be the length of the tube. You've got one full wave inside of there. Okay, so let's talk about the second overtone, or the third harmonic. Alright, so we're going to have an antinode on each end, just like before. How many nodes do you think? We're going to have 3 nodes. So fun. So let's put one in the middle, and we'll subdivide like that. They're going to be evenly spaced. So now we're going to go up, and down, and up, and out. And this one is going to be doing the opposite. Easy money. Okay. So, question is, how does the wavelength relate to the length? Do we have a full wave? Yes, we've got more than a full wave. But what? So let's do the same kind of thing. Let's keep it simple, right? So if I follow this until I get a full wave, it's going to go until here. Alright? That is a full wave. What percentage, or what fraction, let's go with fractions, fractions are better. What fraction of the pipe is that? Is it half? Is it a third? Is it a quarter? Well, what do you think? Ooh, text your vote in now. Alright, anyways, so let's think about it this way. We've got 1, 2, so this is going to be 2/3. Alright, how do I know it's 2/3? Alright, because this one right here is half of a wave. I'll circle it. That way it looks a little more different. This is half a wave. So you have one there and one there. You've got 3 half waves, and you want 2 of them. So it's 2/3 times L. Ta-da! Okay, there is a pattern here. Can you figure it out? So we're going to talk about the nth harmonic, which is the n-1 overtone. Okay? So this has how many nodes? This will have n nodes. Alright, don't worry about the picture because you can't draw a picture. But looking at the formulas, what is the pattern? How did I change from this to this? What changed from this to this? And how can I predict what will happen here? Alright. Do you have a guess? Hopefully you wrote your guess down. Anyways, L is going to be there for sure. But what's going to happen? What you're going to get is you're going to get 2 over n. Okay, but Mr. Keeney, that doesn't match for the first ones. Well, au contraire, mon frère, because this is 2 over 1L, and this one is equal to 2 over 2L. It just reduced. Weird. So that is the formula for a open-end resonator. You don't have to memorize that formula because who likes memorizing things anyways? But you should at least be able to recreate the drawing to figure that out. Alright, that's the goal. So let's do some practice problems. Speed of sound in air is found to be 340. Determine the fundamental frequency of an open-end column that has a length of 67.5 centimeters. Okay, so let's draw a picture here. So here's my 67.5 centimeter long tube. Now we want the fundamental frequency, so we're going to draw a picture of the fundamental frequency, which is just going to look like that. Ta-da! Fundamental's first harmonic, right? Okie dokes. So judging from this is half of a wave right there. So I know that my wavelength is going to equal 2 times my length, right? Because the length is equal to half the wavelength. Then what do I need to do? Well, I know that V is equal to lambda F, right? Remember your wave formula, the one that you're going to use a lot. So then V is going to be 340. It's going to equal lambda, but lambda is going to equal to 2 times L times F. So we're going to solve for L. And you could have done this in multiple steps too, but I like to flex, bro. So what's F going to equal? F is... Wait, oh, sorry. We know what L is. We want the frequency. L is going to equal 67.5. Oh, but that's in centimeters. We have to change it to meters, don't forget, because this one is in meters. So we're going to have some quick maths here. 340 divided by 0.675 divided by 2 is equal to 252 hertz. Nice. That's about a little flat for a C. Something like that. Anyways, let's do one more time. Determine the length of an open-air resonator required to produce a fundamental frequency of 480 hertz. The speed of waves is known to be 340. Okay, same kind of dealio. Alright, let's draw a picture because I forgot all the formulas already. Oh, see if you can do it too. But I'm going to draw a picture of your fundamental frequency, which is going to look like this. Ta-da! Hey, because it's the fundamental, again, lambda is going to equal 2L. I don't have to think too hard about that. V is going to equal lambda F. So that means that V is going to equal 2 times L times F. Now, we know that F is going to be 480. We're solving for L. This is 2. And V is going to be 340. So I'm going to take my 340 divided by 2 divided by 480. And I'm going to get L is equal to 0.354. Now this is in meters. Let's change it to centimeters to be normal. 35.4 centimeters, which would be more useful for the real world here. Ta-da! So that's how open-air resonators work. Hopefully you're doing okay, because tomorrow we're going to close it up here.